everybody. So now what I'm going to do is velocity selector. So before I do velocity selector, we talk about this, right? Magnetic force, which we talk about is this. This is the magnetic force. This is the magnetic force and electric force. Alright, these two are very important concept here, right? So now here in this case, what I'm going to do is, instead of a charge just moving in a magnetic field, I allow a charge to move in a what we call as a cross field. What we call as a cross field. Cross field is one where magnetic fields is perpendicular to electric field. I have an electric field as well as magnetic field, where electric field and magnetic fields are perpendicular to each other is what we call as a cross fields. Alright, so in these diagrams I have here, this is the magnetic field is along a z-axis and electric field is along a y-axis. Alright, so this is what we call as cross fields, and I allow a charge to move along x-axis. Right, charge is along, so I say a magnetic field is along z-axis, electric field is along y-axis, and then velocity is along x-axis. This is what I have, right? And then what is going to be what is the path of a charged particle, right? So this is what I have. So we would like to write here, this is the force, this is the total force. So total force is equal to electric force and plus magnetic force. And this is what I have. Electric force is equal to QE and magnetic force is equal to what I have here. Alright, so now I would like to show you this in vector notations. What about the direction of electric fields? So electric field can be represented the electric field. Electric field is along a y-axis. The y is a j cap, unit vector, right? And what about magnetic field? Magnetic field is given by k cap. What about velocity? Velocity is represented by velocity along x-axis. This is the vector notation in a unit vector notation, right? So now I would like to give you this, right? Before I do this, whenever we talk about this unit vector notations, I say that this is just for your understanding. I'm writing here. Maybe you have learned this in class 11. I cross j is what we call as k cap, and j cross k is what we call as I cap, and k cap cross I cap is what we call as j cap. Alright, this is what I have. This is, and it's just the opposite, right? If I say if j cross I is minus k cap, this is anti-commutative, learned in class 11, right? K cross j is minus I cap, and I cross k is minus j cap. So this you should know, right? I think you have learned this in class 11. Alright. Now having this, what I'm going to do is now, what is the total force? So total force is equal to Q E where is J, right? This is J. Alright. Plus, what about this? This is equal to Q. What about V? V is I cap, and then cross B is equal to K cap. Alright. So now F is equal to plus Q V B I cross K. Alright, so what is I cross K? I cross K is minus J. I cross minus j cap. So look at here. So I am going to show here the direction of a magnetic force, electric force is up. This is along a j cap, and the direction of magnetic force is down. This is a minus j cap. This is the minus j cap, right? So now, looking at these equations, I can tell you that whichever force is greater, the charged particle bend towards that force. If I say if electric force is greater and the charge goes along this is the path of the charge. If electric force is greater than magnetic force, and if I say charge goes along these directions, alright, let's say charge goes along these directions. If electric force is less than magnetic force, so this is the point, right? Electric force is less than magnetic force. I'll just take the magnitude only, right? Okay. Now, if two forces are equal, right? If I say if FE is equal to FB, if FE is equal to FB, then path is going to be like this. This is the path. This is the path. So FE is equal to FB, and net force is going to be 0, right? Net force is going to be 0. So therefore, this force is going to be 0. This is what we call underivative. Charge neither goes along this, no, so it will go underivative. The path of a charged particles underivative. Charge move, alright, without any deviations. Alright. So having this, now I will take this. If F is equal to 0, if Fe is equal to Fb, then I write here this is equal to QVB, Q cancel out, V is equal to E by B. This is very, very important. This is what we call selective velocity, right? So, with what velocity charge undergoes underivative path? This is the velocity which is equal to the ratio of electric field and magnetic fields. If the velocity of a charged particle is equal to ratio of a magnetic field and an electric field, then magnetic force is always equal to electric force. So therefore, charge moves without any deviation. So this is and this is what we call why selective velocity. If I send the millions of charged particles in a cross fields and I just tunes, alright, and then such that the particle having velocity v, charged particle having velocity v will move underivative. So this is how we could select a particular moving charged particles. How we are going to select a particular moving charged particles? Alright, I just fix my charged particle velocity using these ratios, and I send the millions of charged particles in a cross fields, and the charged particles having these velocities could go without any deviation. So this is what we call as a selective velocity. This is very, very a huge application. Application in many nucleoscience, nucleophysics devices, right? So this is what we talk about velocity selector, right? Now I would like to do how to find out magnetism. So far we were talking about effect. Alright, effect means the force. Alright, effects of moving charged particles, right? So that is, it experiences a moving charged particle experience a force in a external magnetic fields, uniform external magnetic fields. So now what we are going to study is how much magnetic field one could produce. Alright, how much magnetic field one could produce. So this is very, very important, and this is, we are going to study this under what we call as a Biot-Savart law. We are going to study this under a law called a Biot-Savart law. This is very similar and to Coulomb's law, right? This Coulomb's law and the Biot-Savart laws are, Coulomb's law is for electric field or electric charge, and then Biot-Savart law is for magnetism, right? So this is what we have, right? All right, so this is what I have. So let's start Biot-Savart law. Okay, let's start. So this is so I'm going to give an example of a Coulomb's law. When we do a Coulomb's law, again I have charge particle which produce a discrete charge particle which produce electric fields, right? Let's talk about Coulomb's law. This is an electric field produced by a discrete charge particle Q. And then an electric field is inverse square of distance between the charge particle and a point where we are going to find out electric field. So Q is a charge. Q is a charge. Now this is now I've given you an example, or I've given you right examples of electric force or electric field or Coulomb's law. Now I would like to do a Biot-Savart laws. This is current carrying wire. So I have a current carrying wire, right? Current carrying wire. Current carrying wire. Having a current I. Having current I. All right. This is what I have. This is wire through which current is passing through it, and here what I'm going to do is I would like to find magnetic fields. Find magnetic field at P. To find magnetic field at P at distance R from current elements, right? Are from current elements IDL or length elements. Length element is a small portion of length dl. Length element dl. This is so like Coulomb's law we choose discrete charge, that is Q. Here in case of Biot-Savart law we choose what we call as current element, right? Discrete, what we call as current element, right? So current elements. Current element. Magnetic, we are going to find out magnetic field due to current element dl. Current element IDL. Current element IDL. Okay. And look at here. What we found is magnetic field at point B. Magnetic field at point B is proportional to I dx. Magnetic field at P is proportional to I dl, and it is also found that magnetic field is inversely proportional, right? Inverse square of distance between P and dl. Inverse square of distance between P and ds. Alright, magnetic field is proportional to IDL. So IDL act as a discrete charge, something like that. And magnetic field is proportional to inverse square of distance between dl and P. Alright, therefore, what I write is this is. Alright. So vectorally, since B is a magnetic field, since B is a vector quantity, I rewrite this vectorally. I can write this proportional signs I dl cross R cube. You may surprise that why R cube, because I put R at the numerator, right? So this is what we have, right? And I remove a proportional sign. This is mu naught 4 pi, and now this is the complete expression of Biot-Savart law, and mu naught is magnetic permeability, in a space, in a free space, in free space. Alright, this is what I have, and the value of mu naught divided by 4 pi is value of mu naught divided by 4 pi is 10 raised to the power minus 7 Tesla ampere meter per ampere. Tesla meter per ampere. This is the value of mu naught divided by 4 pi. This is what I have. Biosival law. Alright, so I'm going to write here again a biosival law. So this is a magnetic field due to a small current elements. This is a magnetic field due to a small current elements. Mu naught 4 pi and the magnitude is going to be therefore direction. Let's talk about directions. Direction is perpendicular to the plane containing DL and R. What is all the magnitude of this? Right, so magnitude is going to be I'm not right here, I just put square sine theta, where theta is angle between DL and R. So R is what we call as this is theta. This is theta. So this is the DLI. Look at here. This is the tangent, and this is the magnetic field. And here we are going to find out. And this is the angle. Theta is angle between. This is the direction of DL. This is the direction of DL, right? So this is what I have. And the direction is also given by a right hand thumb rule. Look at here. So how you have to do is you have to do like this. L cross B. This is L cross R. Where is R? This is L. Look at here. This is L, and you go curl your finger towards R. What is the direction of magnetic field? Into the plane. Direction of magnetic field is how it is going to be into a plane. This like this. Look at here. This is L directions. R into the planes. Again, I am repeating. L DL and DLR. Direction of thumb is the direction of magnetic field. So this is how we represent, right? And now we would like to do a small few cases here. So I say if theta is equal to, let's say if theta is equal to 0, that is if R is along DL, then dB is 0. So this tells that there is no magnetic field along a length element directions. No magnetic field along a length element directions. If theta is 0, why? Because sine 0 is 0, right? So dB is going to be 0. Why dB is 0? Alright? Sine 0 is 0. So this tells that there is no component of a magnetic fields. There is no component of magnetic field along a length element direction. It must be always perpendicular to the L, DL, right? So if I say if theta is equal to 90 degree, that means if R is perpendicular to DL, then dB is equal to mu naught I dl divided by 4 pi R square. So this is the case. This is the case. This is very, very important. So what you have to understand here is no magnetic field. There is no magnetic field component along a direction of length element. It is always perpendicular to the DL. Alright, so that is the point. Okay, this is all about a Biot-Sievert law. This is all about Biot-Sievert. Even I will give you an example of a Biot-Sievert law. Alright. If I have a straight current wire, look at here, I'll do this for this, right? If I have a straight current wire, if I have a straight current wire and the magnetic field, what about magnetic field here? I choose a small length element GL, current I. What is here, right? This is R, this is R, I, L. Look at it, L cross I. Look at here. That angle is 90 degrees, so this is into the plane. Now, if I have here, direction of R is in this direction, I is this. So, what about this, right? Alright, look at here, this is DL directions. I'll put here vector sign. DL directions and DL directions and like this. Alright, so this is out of plane. This is out of plane. This is out of plane. Alright, so this is what I have, right? So you do some practice. So therefore, what we are going to get is we are going to get a circle like this. This is the magnetic field. Alright, this is what we call about biospherical law, right? So I'm going to stop here, biospherical law. Alright, so next class we are going to use this biospherical law to find out magnetic field, central current.